So hello everyone, my name is Joseph Tallan. I work under Dr. McCloy here, and my primary area of focus is on the optical materials and things. Is everything all right?
Can we hide that?
Cool. Yeah.
Box somehow?
It's
I mean, you should write it down.
on the top left corner.
There you go.
Okay, perfect. So yeah, I was saying my primary area of interest right now is optical ceramics. Primarily, we've been working with yttrium oxide. So just as a brief introduction, the reason why we're interested in yttrium oxide primarily is it has excellent optical properties. It can achieve very high transmittance across a pretty wide window. You can get it from, I think, about 252 nanometers all the way up to 8 micron as a cutoff. So it has a very wide range as both a visible light window, but also as an IR window, which is how it's been used historically. It has excellent thermal properties. The coefficient of thermal expansion is quite low, which makes it very suitable to very high temperature properties, especially or situations, especially in hypersonics and things like that. Excellent chemical resistance, especially in extreme environments. There's been talk of using it in the nuclear industry and other industries where they can avoid a lot of chemical attack. High abundance, it's a relatively inexpensive material. It's usually a byproduct of things like neodymium and other rare earth magnet mining processes, which makes it easier to come by than some of the much rarer rare earth oxides. It's also non-toxic to some degree. I mean, it can become toxic if you make nanoparticles and breathe them in, but generally speaking, it's a more friendly material to work with. And finally, it has a proven history. It's been in development since the 1960s. There are a variety of methods of synthesizing transparent yttrium oxide ceramics and things like that. So the first step that we had to go through when producing transparent ceramics is powder characterization. So the first thing that we did was we got some 99.999% or 5N pure yttrium oxide from Alpha ASAR, which is now Thermo Fisher Scientific. We did SEM imaging on it to see exactly what it looked like. We found that the average particle size was approximately 3 to 5 micrometers. And what we found was that the particles that we were using have this very, very rough surface with a lot of fracture edges, most likely from the way it was manufactured and processed. It was probably milled down to this particle size. So the very irregular geometry ended up posing some problems that we'll get into later. But yeah, the other thing that's important to see here is because it's one, a large powder, and two, it was most likely milled instead of chemically synthesized, there's a very low degree of agglomeration in the powder. It doesn't tend to really join with itself. It's a lot of diffuse particles instead of having a few larger or many small particles combined into singular larger particles. So the first thing that we did after we looked at it with the SEM was we did powder characterization. We wanted to see what is the phase of it. Now with yttrium oxide, it's typically in the cubic Bixbyite phase, which is exactly what we want, because when you're making optics, if you have a non-cubic phase, you run into birefringence and things like that. And then if your grains are not perfectly aligned or you're not working with a single crystal, you'll get distortion of your image. So what we found was we had pure cubic Bixbyite phase, no secondary phases, although just because it was pure cubic Bixbyite doesn't mean that there aren't other contaminants. So we did Raman spectroscopy on it, and we found that there was the presence of primarily neodymium oxide and erbium oxide, which we were able to see with the rare earth luminescence. It's important to note that this luminescence isn't really a quantitative measure. Generally speaking, we can't tell how much of it we have. We just know that we have some of it. And it's very important to understand what contaminants you have, because in optics, a lot of your optical properties are extrinsic. They're not necessarily based on your host material, but based on impurities and porosity and things like that. So to go into our experimental procedure, this is our hot uniaxial press that we use. If you guys are familiar with optical ceramic processing, there's a few different techniques that are widely used. There's hot isostatic pressing, there's hot uniaxial pressing, there's vacuum sintering. In our particular case, we use hot uniaxial pressing because, again, it's a pretty tried and true method. It's relatively simple. It's a lot faster than vacuum sintering, which can take many, many hours, which can be very energy intensive and expensive. And the general process flow is that you have a die, you line your die with some type of foil to prevent your powder from sticking to the inside of the die after the sintering process. You load your die, you compact your powder gently initially. And we found that it was very important to compact the powder in a specific way, because compacting it too vigorously and things like that can lead to materials from the die becoming embedded in the powder and thus in your final sample. Then once you've loaded your dye, you pull a vacuum and you begin heating. And then during the heating process, no matter how much calcination and other stuff you do, inevitably you get some off-gassing, especially at very high temperatures. You start to actually lose yttrium and oxygen off of your sample matrix. And that having to pause to maintain vacuum is actually a huge problem, because every time you pause, it increases your length of your sintering window, which will then allow you to have excess grain growth, which is something you have to be aware of. And then you cool to room temperature. You'll see in the next slide that we tried to use a relatively high cooling rate to almost quench the grains and stop grain growth as much as we could, because we were targeting smaller grains. And then after you've done all that, you can extract your pellet from your dye, and then you can grind, polish, and characterize it. So on previous work we've done, we found that sintering of yttrium oxide worked best for us between 1600 and 1800 degrees Celsius. So we knew that that was kind of the target region we wanted to work in. We'd also sintered all of our previous samples at 40 megapascals of uniaxial pressure. But one of the process parameters we hadn't played around with was, in theory, our dyes can go up to 100 megapascals, and would increasing the pressure during the sintering process decrease our porosity, have any effect on our grain size or grain orientation and things like that. So we chose 3 process temperatures and 3 process pressures to work with to make, in theory, a total of 9 pellets. So we chose 1650 C and 1700 C and 1750 C for our temperatures, and then 40, 60, and 80 megapascals for our sintering pressure. And after sintering, what we found was that even at 1750 degrees C, we had a lot of problems extracting pellets. It seemed like at 1750 degrees C, the yttrium oxide would kind of eat through the graphite foil and basically become welded to the inside of the dye. And then because it was welded to the inside of the dye, during the heating and cooling process, it would end up cracking the pellet. And then when it was extracted from the dye, you got this, which was kind of a destroyed pellet. So unfortunately, we weren't able to synthesize any pellets at 1700 degrees C. So all 6 of the pellets that we did get were at 1650 and 1700 degrees C respectively. What we did find was that there was really no contribution to pressure to how hard it was to extract full pellets from dyes. I individually or personally was expecting that things sintered at higher pressure would be harder to extract from dyes, but we found that that was not the case. It didn't really have an effect. And after we extracted our pellets, we ground them with silicon carbide paper to remove any, surface graphite that was left over from the sintering process. And then we polished them with diamond polish to a mirror finish. Approximately 1 micron diamond polish was used. And as you can see in a few of these, I think 3 of them, you can see kind of cracks in the pellets. It's important to note that those cracks were all developed during the polishing process, either by user error and catching the edge of a pellet on the polishing cloth and kind of cracking it off. Or we had problems with excess heat during the polishing process, and the kind of very rapid heating from friction between the pellet and the polishing medium ended up cracking a few of the pellets. And then moving on, we got to the characterization of our pellets, and we looked at our optical properties in both the IR and the UV visible region. You can kind of see blown up pictures of these graphs here, and you can see that especially at 1650 degrees C, we got significantly higher performance in the IR region than we did in the visible region. And there's an important reason for that, and that's that during the sintering process, the graphite kind of pulls oxygen off of the yttrium oxide, and you form these oxygen vacancies, which are color centers in the material. And these are more absorbing in the visible region, and that kind of degrades your optical properties in the visible region. The other primary thing is porosity, which in the IR region, the porosity is the primary limiting factor for our transmittance measurements. And you can see there's some peak assignments here. So we can see at the 4.3 micron region here, we have a little dip in a few of our samples. That's simply due to atmospheric CO2 in the chamber that we were measuring our samples in. We also have a dip right here at 6 microns in one of our samples, which is due to carbon monoxide. And then we kind of have a broad stretch right here between 2.5 and 4 micron that's due to an OH impurity, which is from alcohol. I swap down the samples every time before putting in the IR measurement system, and I think I just didn't wait long enough for the, yes.
What's the difference between the left and the right columns?
So on the left side, you have the visible region from 300 nanometers to 800 nanometers, and then on the right side here, you have the IR region right there. And as I said earlier, we were able to attribute the majority of our optical losses to excess porosity and large pores. So after we just assessed the optical properties, we wanted to look at both the density and also the XRD again to see if any secondary phases happened. We knew that we had some rare earth contamination. We were curious if that rare earth contamination would precipitate out and form a measurable secondary phase, but we noticed it didn't. And when we're doing our density measurement, we measured it two ways. We measured it by pygnometry with a helium gas pygnometer and also with just water displacement Archimedes style density. We found very good agreement between these two numbers, which tells us that our porosity is likely closed off and that neither water nor helium or anything is able to get into our sample where the actual pores are. And what's interesting is the nominal density of yttrium oxide is 5.01 grams per centimeter cubed. And usually what I've heard is if you get above 99.5% density, so to speak, you're usually kind of in the sweet spot for when your optical properties start to become relatively good. And what we found is that just a simple density number is not enough to really tell us what we need to know. It's not actually the density, but more a matter of the number of pores and the size of those pores. You could have a significantly lower density with very, very small pores and be fine. What you can't have is have a very high density with a few very large pores like we have. And you can see in these IR microscope images that we took, both the difference in grain size between samples sintered at 1650 degrees C and those sintered at 1700 degrees C. The samples sintered at 1700 C had significantly larger grains, but also you're able to see the pores in these samples. In all cases, the pores are approximately 1.5 micron, which relative to the incident light's wavelength is more than enough to cause a very, very high degree of scatter in our samples. And we believe that that porosity is primarily from the shape and morphology of the particles and just the spacing between the particles during the sintering process, and just the sintering process not really having enough time for material to diffuse and fully close off those pores. And then finally, one of the interesting things that we were also able to do is we were able to track the rare earth luminescence in our samples. We were actually able to see our grain boundaries based on the rare earth luminescence. So right here, we have a kind of highly visible grain boundary that you can see. And then we've done rare earth mapping with the 785 nanometer laser. And you can clearly see where you have a much higher concentration of this neodymium luminescence here. So it's very interesting to be able to see that. And we can also see that not all grains in our sample have a homogeneous amount of neodymium oxide or neodymium 3+ ions. We can see that we have one grain that's much higher in neodymium concentration, and then one grain that's much lower in neodymium concentration. So it's important to see that. And then in conclusion, we were able to synthesize transparent Y2O3, although the optical properties are not quite where we want to be to do actual mechanical testing. We'd ideally nail the optical properties, and once the optical properties have been nailed, we'd move on to the actual mechanical testing. So the biggest thing that we need to work on is we need to control our porosity in the samples. We need smaller pores, we need more regular pore structure. And the way we intend to go about doing that is by utilizing smaller powders. We have nano powders that we're intending to use in our next line of synthesis. The challenge with using nano powders is that they're much more difficult to work with. They tend to agglomerate a lot more. They do not flow nearly as well and things like that. So to counteract that, we're going to improve our sample powder treatment, and then we're also going to employ a more advanced sintering process with more holds and things like that in the process to try and improve our further densification. And to conclude, I would just like to thank the National Center for Manufacturing Sciences. I would also like to thank Dr. John McCloy, Chris Wilkins, and Sam Karcher for helping me with my research. And then, are there any questions? Yes.
What was the two different kind of density methods that you used?
So we have water displacement method where you submerge your sample in this water. You can do alcohol or a lot of other solvents depending on what you're working with. And then we also had pygnometry where you have a chamber, you put your sample in a chamber, and then you diffuse gas into that chamber, and you can determine the volume of your sample based on that. And then you just divide the volume or your density or the mass by the volume of the sample, and you're able to achieve your density that way.
Okay. But the pygnometry still doesn't account for closed pores, correct?
Yeah, if your porosity is closed off and the pores are, or the channels in your material is too small for the helium to get into, then you have no way of really knowing that or seeing that, so to speak. Whereas if you have a lot of surface defects and things like that, then the helium gas can be able to get into places that the water is too large to get into, so to speak. And you might see a significant difference, or if you have a lot of interconnected channels in your material or something like that, water probably won't be able to get into them. But helium gas will, and you'll be able to see, and then you'd see a much closer theoretical density than you would otherwise.